Vehicles are learning to move without making a sound. The hidden evolution of thrustless vehicles is quietly unfolding. A revolution built not on fire and thunder, but on invisible forces that challenge our basic understanding of physics. This video will reveal the secret history and groundbreaking engineering that is fundamentally reinventing motion itself. You will learn how silent innovations are poised to reshape our cities and our relationship with the environment. Why have these radical ideas remained in the shadows for so long? And what does a world without engine noise actually look like? Are you ready to see how motion will be redefined in your lifetime? Leonardo da Vinci's notebooks reveal more than just art. They contain intricate sketches of aerial screws and machines that flap like birds, all searching for a way to fly without the violent expulsion of thrust. These were not just flights of fancy, but early blueprints for a different kind of motion, one that worked with the air rather than fighting against it. Centuries later, figures like Nikola Tesla would pick up this same thread, conducting secretive experiments in his Colorado Springs laboratory. He was obsessed with the idea of harnessing the Earth's own energy, of propelling vehicles wirelessly through the air using electromagnetic forces. He called it electrogravitics, a concept so far ahead of its time that it was largely ridiculed and forgotten. Yet these pioneers, from Renaissance inventors to misunderstood geniuses, shared a common vision, a persistent dream of movement that was both seamless and silent. Their ideas were the first cracks in the solid wall of conventional physics, suggesting that maybe we did not need to push against the world to move through it. Why did these brilliant concepts remain on the fringes for so long? And what crucial pieces of the puzzle did they possess that we are only now rediscovering? The core idea is deceptively simple, yet it overturns centuries of engineering dogma. Traditional propulsion, from roaring jet engines to spinning propeller blades, obeys a straightforward rule: for every action, there is an equal and opposite reaction. You push something backward and you get pushed forward. It is a system built on forceful expulsion, a constant battle against the medium it moves through. Thrustless propulsion abandons this entire conflict. It does not push against anything. Instead, it seeks to persuade the environment to do the work. Think of it not as shoving your way through a crowd, but as the crowd itself parting before you and flowing around you. A thrustless vehicle might create a bubble of low pressure directly in front of it, allowing the higher pressure behind to gently push it forward. It could generate intricate wave patterns in the air or water, effectively surfing on these self-created ripples. Another method involves manipulating electromagnetic fields, not to throw anything out the back, but to create a subtle gradient that the vehicle simply slides down, like a leaf caught on a gentle, invisible breeze. The absence of exhaust is what makes it so profoundly silent and clean. There is no fiery plume, no blast of heated air, no spinning rotor to chop through the atmosphere. This is not merely a quieter engine. It is the complete eradication of the engine's most fundamental signature. For engineers, this shift is monumental. They are no longer designing powerful thrusters, but delicate force manipulators. Control becomes a matter of fine-tuning fields and balancing pressures, a dance with physics that is far more subtle and complex than simply opening a throttle. This is the true reinvention of motion, moving from a philosophy of brute force to one of elegant influence. This quiet revolution in physics demanded an equally radical revolution in the stuff things are made of. For decades, the dream of thrustless motion was trapped on the drawing board, a beautiful idea waiting for the tools to become real. That toolmaker has been materials science, working in the background to hand engineers the keys to a new world. Consider metamaterials, substances engineered to have properties not found in nature. They can be designed with a negative refractive index, meaning they can bend electromagnetic waves like light or radio waves in completely unnatural ways. This is not like a lens focusing light. It is more like a cloak that can redirect waves around an object, or a surface that can shape an invisible force to pull, not push. Then there are high-temperature superconductors, materials that can conduct electricity with virtually no resistance, and they do not require impossibly cold temperatures to function. This breakthrough allows for the creation of incredibly powerful magnetic fields that just sit there, humming with potential while consuming a tiny trickle of energy. These fields can be the invisible rails a vehicle slides along, or the gentle gradient it descends. Finally, picture the very skin of a vehicle coming alive. Shape memory alloys and piezoelectric composites can twist, expand, or ripple on command. A wing is no longer a rigid structure, but a dynamic, morphing surface that can generate waves in the air itself. It might ripple like a fish's tail or bulge to create a pressure differential, all without a single moving part in the traditional sense. These materials did not exist in a practical form just a decade or two ago. Their sudden arrival transformed thrustless propulsion from a theoretical puzzle into an engineering challenge. The most visible vehicle prototypes capture our imagination, but the silent, painstaking work in materials laboratories is what truly built the foundation for this new age of motion. And that foundation is still being laid, brick by invisible brick, opening doors to possibilities we are only beginning to walk through. High above our heads, an invisible river of energy flows silently through the atmosphere. The Earth itself carries a natural electric charge, creating a voltage difference of about 100 volts for every single meter you climb upward. It is a pervasive, untapped power source that has been there all along, and engineers are now learning to sail upon it. The key lies in high-voltage electrodes, tiny structures on a vehicle that create an intense electrical field. This field is so strong it can tear electrons away from air molecules, creating a cloud of charged particles or ions. Once these ions are created, they are violently repelled by the electrode, shooting away in one direction. And just like a person stepping off a small boat and onto a dock, the act of pushing these ions away pushes the vehicle in the opposite direction. This is the principle of electroaerodynamic propulsion, a method that creates an electric wind for thrust. The entire process is breathtakingly silent. There are no spinning rotors, no roaring jets, just the faint, ozone-tinged whisper of air molecules being charged and accelerated. Recent experimental aircraft have managed to stay aloft using nothing but this phenomenon, drawing power from onboard batteries to sustain this gentle, continuous push. The efficiency of these systems has been climbing steadily, transforming what was once a laboratory curiosity into a viable pathway for small, silent drones and eventually larger vehicles. Imagine a delivery drone that approaches your window with the quiet grace of a falling leaf, or an aerial camera that can observe wildlife without causing a single animal to startle. This is the profound beauty of the system, its elegant simplicity. Motion is achieved not through complex mechanics, but through the careful orchestration of an invisible force that has surrounded us all along. Sound itself has become a silent engine. We often think of sound as a source of noise, a pollutant to be managed, but engineers have turned this perception on its head. They are now using the pure energy of sound waves to lift objects directly into the air, defying gravity without a single puff of thrust. This is acoustic levitation, a phenomenon that feels like magic but operates on a precise principle called acoustic radiation pressure. When sound waves are perfectly tuned and aimed at each other, they create a standing wave, a pattern of intense pressure that seems to stand still. Within this pattern are specific points, called nodes, where the pressure is so low that it can cancel out the pull of gravity. A small object, like a droplet of water or a piece of foam, can be caught in one of these nodes, held perfectly suspended in mid-air as if by an invisible hand. The real breakthrough comes from controlling these patterns, by carefully adjusting the waves emitted from an array of ultrasonic transducers, which are devices that create sound frequencies too high for us to hear. Researchers can make the pressure nodes move. They can shift the entire standing wave pattern, gently carrying the trapped object along with it. It is like having an invisible conveyor belt made of nothing but pressure and vibration. This is how a small, thrustless vehicle can be silently propelled forward, riding a wave of sound it cannot even hear. While today we see this technology lifting only tiny components in laboratories, the principle is what matters. It proves that motion can be born from pure harmony, from the careful orchestration of forces we normally cannot even see. The roar of an engine is replaced by an inaudible hum, a silent command that persuades the air itself to do the lifting and the carrying. This acoustic approach offers a glimpse into a future where the most powerful forces are also the quietest. Magnetic forces are now being woven into the fabric of motion itself. While the familiar hum of a maglev train represents one application, a far quieter revolution is unfolding in the realm of passive magnetic systems. The key lies in diamagnetic materials, a special class of substances that naturally repel magnetic fields. Think of how two identical poles of a magnet push away from each other, but this repulsion is an innate property of the material itself. When you combine these materials with powerful permanent magnets and high-temperature superconductors, something almost magical happens. You can create a platform that levitates completely stable without drawing any power at all. It just floats suspended by an invisible force at room temperature. This is not science fiction, it is a working laboratory reality. The principle extends beyond simple suspension. Engineers are now programming intricate magnetic field gradients, essentially shaping invisible hills and valleys of magnetic force. A vehicle can then surf these pre-arranged magnetic waves, propelled forward without any physical contact or the constant energy drain of traditional electromagnets. The system only needs a small amount of power for guidance and control, not for the fundamental act of levitation. This shift is monumental. It transforms the very economics of motion. Imagine a citywide network of goods gliding silently on these magnetic currents. Their energy consumption so minimal it rivals the efficiency of the most carefully designed passive systems. This is the next logical step in our journey beyond thrust, where the path forward is not paved with fire and noise, but etched in silent, persistent fields of force. Nature itself is the original master of silent motion, a living library of thrustless engineering perfected over millions of years. Look at a maple seed as it falls from a tree. It does not drop like a stone but spins gracefully, auto-rotating on a single, curved wing. This slow, controlled descent is a form of flight without any thrust at all, using the interaction between its shape and the air to govern its fall. Engineers have directly mimicked this design, creating small, winged sensors that can be released high in the atmosphere to drift and spin their way down, gathering data over a wide area without a single motor. Then there is the jellyfish, a creature that moves through water with an ethereal pulse. It does not push water backward in a jet. Instead, its bell-shaped body contracts, creating a spinning ring of water, a vortex that rolls behind it. This vortex generates a region of low pressure in front of the jellyfish, effectively pulling the animal forward. Researchers have built soft, robotic vehicles that replicate this exact motion, pulsing silently through the water by creating and riding their own self-generated vortices. But perhaps the most astonishing natural example is the spider. On a calm day, you might see a spider suddenly take to the air, ballooning on a strand of silk. For centuries, we thought they were just passive passengers on the wind. We now know many spiders actively sense the Earth's natural electric field. They raise their abdomens, release their silk, and use electrostatic forces to lift off and glide, truly sailing on an invisible sea of energy. Inspired by this, engineers have developed tiny, wingless gliders that use charged materials to electrostatically grip and glide on atmospheric fields, moving through the air without any moving parts. These biological systems are not just curiosities, they are blueprints. They prove that the most efficient and elegant ways to move often involve not fighting your environment, but collaborating with it. This biomimetic approach is unlocking a new design philosophy, one where the answers were not hidden in a textbook, but were floating in the ocean and falling from the trees all along. This silent orchestration of forces demands a conductor of immense speed and intelligence. The subtle interplay between a vehicle's shape-shifting skin and the invisible magnetic currents it rides is a dance of thousands of variables, all shifting in milliseconds. No human pilot could possibly manage such a complex performance. This is where artificial intelligence enters the stage, not as a mere assistant, but as the essential maestro of this new physics. Machine learning algorithms are trained in vast digital worlds, running through millions of simulated flights. They learn through trial and error how a microscopic change in an electromagnetic field will alter the vehicle's pitch, or how a slight ripple in its surface can amplify an acoustic wave for forward motion. They are not programmed with rigid instructions. Instead, they learn the hidden grammar of these silent forces, becoming fluent in the language of pressure gradients and magnetic fields. In real flight, these neural networks process a flood of sensor data, making constant, tiny adjustments to thousands of parameters at once. They maintain perfect stability by anticipating the air's response, balancing on forces that are inherently unstable. The vehicle's control system becomes a predictive mind, not a reactive one. It knows how to shape the environment before the environment has even finished shaping itself around the vehicle. This is the quiet partnership enabling the entire revolution, the fusion of computational intelligence with physical elegance. The machine does not just fly, it learns to persuade the very air to carry it. High above the city, a new kind of aircraft glides with the silence of a shadow. This is an ionocraft, a vehicle that flies not by pushing air, but by persuading it to move. Its wings are not wings at all, but intricate arrays of fine wires and collector plates. When a tremendously high voltage is applied, the air around those thin wires can no longer hold itself together. It tears apart, creating a visible purple glow of atmospheric plasma, a cloud of charged particles. These newly born ions are immediately and violently repelled by the wire, shooting downward toward the collector plate at tremendous speed. With every ion pushed downward, an equal and opposite reaction pushes the entire craft upward. This is momentum transfer in its most direct and elegant form. A silent, continuous push generated by an electric wind. The only sound is a faint, ethereal hiss, the whisper of air molecules being torn apart and accelerated. There is no fire, no spinning rotors, and no exhaust. The system is breathtakingly simple in its principle, converting electrical energy directly into lift without a single moving part. For decades, this was a fascinating laboratory demonstration, capable of lifting only a tiny, lightweight frame a few inches off the ground. The power required was immense, and the thrust produced was minuscule, but recent breakthroughs in high-voltage electronics and lightweight materials have shattered those old limitations. Engineers have dramatically increased what is known as the lift-to-power ratio. Modern prototypes are no longer curiosities. They are achieving efficiencies that suggest practical vehicles are within reach. This leap in performance transforms the ionocraft from a scientific toy into a potential blueprint for urban mobility. Imagine a personal commuter vehicle that rises from your driveway with the quiet grace of fog lifting from a field. It could navigate the tight corridors between buildings, its only emission being a gentle breeze. The absence of noise pollution alone would fundamentally reshape the soundscape of our cities, replacing the constant drone of engines with near silence. This technology represents perhaps the purest form of thrustless propulsion we have yet developed. It sidesteps the entire history of mechanical complexity, offering a vision of motion born not from combustion, but from charge itself. The path forward is being written not in fire, but in the silent, persistent flow of ions. Below the familiar world of magnets and metals lies a layer of reality governed by the strange rules of quantum physics. Here, a phenomenon called quantum locking allows objects to float not just above a magnetic field, but locked perfectly within it, as if frozen in space. This is not simple repulsion, it is a total expulsion of magnetic fields from the material itself, a property known as perfect diamagnetism. When certain ceramic materials are cooled to incredibly low temperatures, they transform into superconductors. In this state, they refuse to let any magnetic field lines pass through them. But instead of just pushing away, they do something far more useful. They trap the magnetic field lines in place. Thin, weak points in the material, called flux tubes, pin the field lines, effectively stitching the superconductor to a specific position in the magnetic landscape. It cannot move up or down, it is locked. This creates a levitation so stable that you can turn the magnetic track upside down, and the superconductor will hang there, defying gravity without a whisper of power. Engineers saw in this bizarre effect a foundation for a new kind of motion. By carefully designing a magnetic track with a textured landscape of hills and valleys, they can create a path of least resistance. A quantum-locked platform does not need to be pushed. It naturally wants to slide down these magnetic gradients, surfing on waves of pure potential energy. The propulsion comes from the shape of the field itself, a silent, persistent tug that requires no physical contact and thus creates zero friction. The only sound might be the gentle hum of a cooling system. For decades, the dream was hampered by the need for extreme cold, often requiring expensive and bulky liquid helium. But the ongoing revolution in materials science is changing that. The development of high-temperature superconductors, which operate at less extreme, more manageable temperatures, is what transforms this laboratory marvel into a practical tool. We are now inching towards systems that could be integrated into real-world infrastructure. Imagine a city where goods glide silently through distribution centers on quantum-locked pallets, their movement guided by nothing more than the invisible topography of a magnetic map. This is the promise of quantum locking, a future where motion is not a fight against friction, but a graceful descent along paths of magnetic force. Even the vacuum of empty space is not truly empty. It is a seething sea of energy, a quantum foam where virtual particles flicker in and out of existence in a constant, chaotic dance. This hidden energy of the universe is now the target for the most ambitious form of thrustless motion yet conceived. The key lies in a strange quantum phenomenon known as the Casimir effect. When two perfectly smooth, neutral metal plates are brought incredibly close together in a vacuum, they are pulled toward each other by an invisible force. This happens because the tiny gap between the plates restricts the types of quantum fluctuations that can exist there. The energy density outside the plates becomes greater than the energy density inside, and this pressure difference pushes the plates together. For decades, this was just a fascinating quantum curiosity, a force only measurable at microscopic scales. But a new generation of engineers is asking a radical question. What if we could structure surfaces not to be smooth, but to be intricately patterned with nanoscale shapes, like an array of microscopic fins or gears? These nanostructured surfaces could manipulate the quantum vacuum in asymmetric ways. One side of a surface could be engineered to experience a stronger Casimir force than the other, creating a net push, a tiny but continuous force in one specific direction. This would be propulsion generated not by expelling anything, but by coaxing a directional force from the very fabric of spacetime. The vehicle would essentially be swimming through the quantum foam of empty space. The challenges are, of course, monumental. These forces are incredibly weak, and amplifying them to a useful scale for a macroscopic vehicle is a problem that may take decades to solve. It requires a mastery of nanotechnology and quantum physics that we are only just beginning to develop. Yet, the theoretical pathway exists. This line of research represents the ultimate frontier, a form of motion so pure it requires no propellant, no medium, and leaves absolutely no trace. It suggests a future where a craft could navigate the void between stars, propelled by the gentle, persistent pressure of nothingness itself. That faint hum you hear might not be from a public lab, but from a facility that does not officially exist. For decades, the true cutting edge of thrustless propulsion was not forged in university workshops, but in the sealed chambers of government and military research. Classified programs, many with roots in the deep freeze of the Cold War, pursued propulsion concepts so exotic they bordered on science fiction. Recently declassified documents have begun to peel back a corner of this secret world, revealing studies with startling titles that speak of gravitational manipulation and inertial mass reduction. These were not thought experiments, they were rigorous, funded investigations into bending the very laws of physics to achieve silent, undetectable motion. The papers describe theoretical frameworks and experimental results that suggest a level of understanding decades ahead of anything happening in the public sphere at the time. They were not just asking if these things were possible, they were calculating how to engineer them. The logical conclusion is as unsettling as it is compelling. If these were the ideas they were willing to declassify, what breathtaking prototypes remain hidden behind higher levels of secrecy today? This pattern of technological drip feeding helps explain a curious phenomenon in the public domain. A concept will languish for years as an academic curiosity, dismissed as impractical, only to suddenly reappear in a corporate or research setting looking remarkably mature and viable. It is as if the foundational problems were already solved elsewhere, and the public race is simply catching up to a course that was already mapped in secret. This hidden history paints a dual picture of our technological timeline. The quiet revolution in motion we are witnessing today may not be the beginning of the story, but the public unveiling of a journey that began in shadow long ago. What other principles of motion, currently deemed impossible, are already being tested in rooms without windows? The secret laboratories no longer hold a monopoly on silent flight. A surge of innovation is now flowing from small startups, where agile teams are turning radical theories into tangible machines. Companies with names like Jump Aero and Volerian are pioneering personal aerial vehicles that look nothing like traditional aircraft. Their designs abandon spinning propellers for something far more elegant, sophisticated wing morphing, and a technique called circulation control. Imagine a wing that can subtly change its own curvature in flight, its surface rippling like living tissue to shape the very air moving over it. By bleeding a thin layer of air over these morphing surfaces, they can energize the airflow, preventing stall and generating immense lift at low speeds, all without the deafening roar of a jet engine. This is flight reimagined as a dialogue with the atmosphere, not a declaration of war. On the ground, other ventures are applying the same philosophy. They are building transportation systems that use magnetic gradient propulsion, where vehicles surf on pre-arranged magnetic fields. The startup environment is the perfect catalyst for this kind of revolution. Unburdened by corporate bureaucracy and legacy thinking, these small teams can pursue unconventional ideas that larger, more conservative companies would deem too risky. They operate on a cycle of rapid iteration, building a prototype, testing it, learning from its failures, and immediately building a better version. This agile process has attracted significant venture capital, transforming what was once a fringe scientific pursuit into a serious commercial investment. Functional prototypes are no longer just computer models. They are real machines taking real, silent flights in hangars and proving grounds. This influx of private funding and talent represents a profound shift, the democratization of thrustless technology. The power to reinvent motion is moving from the sealed rooms of classified programs into the open, collaborative world of entrepreneurs, accelerating our journey toward a future where the sky and the street belong to everyone. A thrusterless vehicle needs a whisper of power, but it must last for hours, not minutes. This is the silent vehicle's greatest paradox, its elegant motion demanding a revolution in energy itself. Traditional combustion engines are useless here, their fiery explosions and spinning turbines fundamentally at odds with a system built on subtle force manipulation. The answer lies not in burning fuel, but in storing and harvesting electricity with unprecedented efficiency. The most immediate breakthroughs are happening in battery technology, specifically with solid-state and lithium-air designs. A solid-state battery replaces the flammable liquid electrolyte with a stable, solid material. This is not just a minor upgrade, it is a complete rethinking of the battery's core architecture. The result is a power pack that is safer, can charge in a fraction of the time, and packs far more energy into the same space. Lithium air systems take this even further, drawing oxygen from the surrounding atmosphere to react with the lithium metal inside. This process mimics how our own lungs work, tapping an endless external resource to dramatically boost energy density. Imagine a personal commuter craft that can travel for hundreds of miles on a single charge, its power source as compact and silent as the vehicle itself. But some engineers are asking a more radical question: why carry all your energy when you can harvest it as you go? They are integrating photovoltaics directly into the vehicle's skin, turning every exposed surface into a power generator. These are not the clunky, blue solar panels you see on rooftops. They are thin, flexible, and incredibly efficient films, woven into the composite materials of the wings and fuselage. As the vehicle glides silently through the sky, its own body is quietly sipping energy from the sun, extending its range almost indefinitely. For applications where even sunlight is not enough, researchers are looking to the skies with another solution: wireless power transmission. A ground-based station could focus a beam of microwaves or laser energy directly onto a receiver on the vehicle's underside. The craft would essentially fly along a virtual power line, a corridor of invisible energy granting it theoretically unlimited range. This approach transforms the very concept of refueling from a physical stop into a continuous, seamless flow. The drive for silent motion has therefore ignited a parallel race for silent power, pushing the boundaries of material science and electrical engineering in ways we never anticipated. Solving this energy equation is the final, crucial step that transforms these beautiful experiments from laboratory marvels into the quiet, ordinary vehicles of our future. The true promise of this silent revolution is not just in how we move, but in the world we leave behind as we do. Thrustless vehicles offer a future where transportation sheds its role as a primary polluter, becoming a gentle, almost invisible thread in the fabric of our cities. Without any combustion process, these systems produce zero direct emissions. There are no exhaust pipes spewing greenhouse gases, no clouds of fine particulate matter to darken the air and damage our lungs. For urban centers perpetually shrouded in a haze of smog, this shift is not an incremental improvement. It is a fundamental cleansing of the atmosphere itself. The air in our busiest streets could become as clean as the air in a remote forest, simply because the machines moving through it are no longer burning anything. The silence is an environmental benefit just as profound as the clean air. The constant, grinding roar of engines and the whine of turbines form an acoustic blanket of stress over modern life, disrupting wildlife, increasing human anxiety, and polluting our sonic landscape. Thrustless transport replaces this noise with a near-silent whisper, or in many cases with absolute quiet. Imagine a city where the morning rush hour is no louder than a gentle breeze, where the sounds of conversation and birdsong are no longer drowned out by the machinery of motion. This reduction in noise pollution restores a natural soundscape, benefiting every living creature within it. Beyond the clear absence of emissions and noise, these systems hold the potential for a radical increase in efficiency. By eliminating the massive energy losses inherent in combustion and mechanical friction, thrustless vehicles can achieve motion with a fraction of the power. When you are not fighting the air but working with it, the energy required to travel a given distance plummets. A comprehensive life cycle analysis, which examines the environmental cost from manufacturing to disposal, suggests that a world powered by thrustless transport would see a dramatic shrinking of the transportation sector's carbon footprint. This positive impact is amplified exponentially when these efficient vehicles are paired with renewable energy sources like solar and wind. The power for their silent journey would come from the sun and the air, creating a perfectly clean, closed loop. This is the ultimate green promise, a technology where sustainability is not a feature that gets added on, but the very core of its design. It redefines progress not as faster or louder, but as cleaner, quieter, and fundamentally in harmony with the world it moves through. The silent sky above our cities is about to become a new frontier for our daily commute. Imagine stepping out of your home not to a crowded street, but to a personal aerial vehicle arriving with the quiet grace of an elevator. This is not a distant fantasy, but the practical future being mapped out by urban planners right now. These thrustless craft, powered by electrodynamic or acoustic systems, will create entire three-dimensional transportation networks layered above the ground. Your journey across a metropolis could be a direct, silent flight from rooftop to rooftop, bypassing the gridlock entirely and turning a 1-hour drive into a 10-minute glide. On the ground, the transformation is just as profound. Magnetic levitation systems could replace rumbling buses and cars with public transit that floats silently along its guideway. These maglev pods would move with such efficiency and quiet that a major transit corridor could operate 24 hours a day without ever disturbing a single resident's sleep. The defining feature of this new urban layer is its silence, making it possible to integrate high-capacity mobility directly into the most dense and sensitive neighborhoods. City planners are already drafting the blueprints for this integration. They are designing landing pads integrated into the architecture of skyscrapers, turning building tops into bustling ports. They are planning for magnetic lanes embedded within existing streets, sharing space with traditional roads during a gradual transition. The most complex challenge is the creation of an aerial traffic management system, a digital control layer that orchestrates thousands of silent vehicles moving in 3 dimensions, ensuring they flow as smoothly as data packets across the internet. This urban integration is the ultimate test for the technology, moving it from isolated prototypes into the complex, lived-in fabric of our cities. It represents the moment when thrustless motion stops being a scientific marvel and starts becoming the invisible, indispensable utility that powers modern life. That elegant silence comes with a steep price in engineering complexity. Scaling a thrustless vehicle from a laboratory proof of concept to a full-sized passenger craft is a monumental leap. The principles of ion propulsion or acoustic levitation that work flawlessly for a tiny drone become exponentially more difficult to control as you increase mass and volume. A personal aerial vehicle requires orders of magnitude more power and a control system of immense sophistication to manage forces that are inherently delicate and distributed. The very subtlety that makes these systems so quiet also makes them challenging to scale up with brute force. You cannot simply build a bigger version of a small prototype. You often have to rethink the entire architecture from the ground up. Energy density remains a persistent bottleneck. Even with the latest solid-state batteries, the energy stored per kilogram is still a limiting factor for long-range travel. While thrustless vehicles are incredibly efficient once in motion, the total energy required for a commercial flight, for instance, must be carried on board. This creates a difficult trade-off between vehicle weight, range, and payload capacity. The technology is racing to close this gap, but for now, it restricts many applications to shorter, more specialized journeys. Perhaps the most invisible yet formidable barrier is the complete absence of a regulatory roadmap. Aviation and automotive authorities have spent a century building safety standards around the predictable failures of mechanical systems, like engine stall or brake failure. How do you certify a vehicle that has no engine, no moving parts in the traditional sense, and whose failure modes might involve the sudden collapse of a magnetic field or a software glitch in its AI pilot? New protocols must be invented from scratch to answer fundamental questions. How do you ensure safe landing during a power loss in a vehicle that has no wings for gliding? What constitutes a safe distance between 2 craft that manipulate invisible force fields? These are not minor adjustments to existing rules. They require a completely new legal and safety philosophy. And finally, there is the human element. Public trust is earned slowly and lost quickly. People are accustomed to the visceral feedback of a roaring engine, the tangible sense of power that comes from traditional propulsion. A vehicle that rises in utter silence, guided by principles they cannot see or easily understand, may initially provoke unease rather than excitement. Building that trust demands more than just technical demonstrations. It requires transparent communication and a gradual, visible record of flawless operation. Overcoming these hurdles is not a single engineering problem, but a multi-front campaign that blends physics, policy, and psychology in equal measure. The final path to adoption will be paved not just with breakthroughs in materials, but with patient collaboration across every domain of human knowledge. A silent vehicle hovering above the street challenges everything we think we know about how things move. This gap between revolutionary engineering and public comfort is the final, and perhaps most human, frontier for thrustless technology. The very invisibility of the forces at work, their quiet elegance, can feel alien compared to the reassuring roar of a car engine or the visible spin of a propeller. We are conditioned to associate power with sound and vibration, a tangible feedback loop that tells us the machine is working. When that familiar sensory input vanishes, it can be replaced by a subtle unease. How can you trust what you cannot see or hear? This skepticism is a natural human response, a protective instinct against the unfamiliar. Educational initiatives are now tackling this head-on, not with dense scientific papers, but with visceral, relatable demonstrations. Engineers are building public test tracks where people can witness these vehicles in action, feeling the gentle hum of a magnetic field or watching an ion craft ascend in utter silence. The goal is to make the invisible physics tangible, to show that the absence of noise is not an absence of power, but a testament to a more sophisticated kind of control. The cultural baggage of science fiction presents a double-edged sword. The image of a silent, hovering craft is instantly recognizable from stories of flying saucers, a connection that sparks immediate fascination, but also layers the technology with connotations of the alien and the unexplained. The challenge is to reclaim this imagery, to pivot the narrative from unidentified objects to identifiable transportation. This requires a new kind of storytelling, one that focuses on the human benefits rather than the arcane physics. We need to stop talking about quantum locking and start showing how a silent ambulance can rush through a city night without shattering the peace, or how a delivery drone can lower a package to your grandmother's porch without startling her. Trust is built on a foundation of transparent testing and clear communication about safety protocols. People need to understand what happens if the power fails, how the vehicle navigates storms, and what systems are in place to prevent collisions. This means openly discussing failure modes and showcasing the redundant systems and intelligent AI that make these vehicles inherently safe. The perception gap will not be closed by a single breakthrough, but by 1,000 small moments of demystification. It is a conversation that must happen in town halls and on city streets, transforming public wonder into public willingness and turning the mystery of silent flight into the mundane miracle of the morning commute. A quiet race is unfolding across the globe, a simultaneous collaboration and competition that is accelerating this revolution. Researchers from Tokyo to Boston share data in open forums, their collective intelligence focused on cracking the fundamental physics that still holds these vehicles back. These international consortia function like a global brain trust, publishing findings and building upon each other's successes in a spirit of shared discovery. Yet beneath this cooperative surface, national ambitions run deep. Governments recognize that the nation which masters thrustless mobility first will secure a monumental strategic advantage, from silent defense applications to dominating the future of global transportation. This dual dynamic is a powerful engine for progress. The collaborative side prevents duplication of effort, allowing the brightest minds to tackle different pieces of the puzzle simultaneously. The competitive side, fueled by national pride and economic potential, ensures a relentless pace of investment and innovation. We see this pattern clearly in history's other great technological leaps, from the race to space to the development of the semiconductor. Both cooperation and competition were essential, pushing the boundaries of what was thought possible. Today, the same forces are at work, creating a rich and diverse technological ecosystem. Different countries are pursuing different core philosophies. One nation might pour its resources into perfecting magnetic gradient propulsion for high-speed ground transport, while another focuses entirely on electroaerodynamic systems for urban air mobility. This diversity of approach is a tremendous strength. It means the final technological landscape will not be a monoculture, but a tapestry of solutions, each refined under unique pressures and priorities. The path forward is being mapped not in one single lab, but across a worldwide network of minds and machines, all striving toward the same silent horizon. The silent revolution is generating a thunderous volume of legal documents. A complex web of intellectual property now surrounds these quiet technologies, with thousands of patents filed across dozens of countries. These are not single, simple inventions, but dense thickets of overlapping claims. One company might hold a patent on a specific metamaterial structure, while another owns the rights to the magnetic field configuration that makes it levitate. Navigating this landscape is like walking through an invisible maze, where a single misstep can lead to a costly infringement lawsuit. This protection is a double-edged sword. On one hand, it spurs massive investment, as companies know their groundbreaking research can be legally defended. The promise of a temporary monopoly on a new form of motion provides the financial incentive to pour billions into research and development. Yet this same system can also slow overall progress. When core technologies are locked away in competing portfolios, collaboration becomes difficult, and engineers can waste years designing around another company's intellectual property instead of building upon it. Alongside these public patents lies a deeper layer of secrecy, trade secrets that protect the true magic behind these vehicles. The public patent might describe a general method for acoustic levitation, but the secret source, the precise manufacturing process for the ultrasonic transducers, or the proprietary control algorithm that maintains perfect stability, remains locked in a vault. This hidden knowledge is often the most valuable asset a company possesses, the key to turning a laboratory principle into a reliable, market-ready product. The global pattern of these patent filings acts as a crystal ball for the entire industry. A sudden surge in patents related to specific high-temperature superconductors signals which materials major players are betting on. A flurry of new filings for diamondoid nanostructures points directly to increased investment in quantum vacuum propulsion. By reading these documents, we can see the silent battles and strategic priorities of every major corporation and nation-state involved. For any company hoping to enter this new market, understanding this intellectual property context is not a side task. It is a matter of survival. They must build their own defensive portfolios, cross-license technologies with rivals, and constantly scan the horizon for new claims that could block their path. This legal framework is the invisible architecture upon which the entire commercial future of thrustless motion is being built. A silent war of words and ideas that will determine who ultimately controls the right to move without a sound. The silent classroom is becoming the new laboratory for this revolution. Universities worldwide are tearing down the old walls between academic departments, building new programs that fuse physics with computer science and materials engineering with quantum mechanics. A student today might not just study aerodynamics, but electroaerodynamics, learning to calculate the lift generated by a cloud of ions instead of a spinning blade. They are exploring the bizarre stability of quantum locking not as a theoretical curiosity, but as a practical design principle for a frictionless bearing. This is not a minor curriculum update, it is a complete philosophical overhaul of engineering education. Interdisciplinary thinking is no longer a bonus, it is the core skill. You cannot design a vehicle that manipulates magnetic fields without a deep understanding of condensed matter physics. You cannot write the control algorithm for its morphing skin without fluency in machine learning and fluid dynamics. The most forward-thinking institutions are establishing dedicated centers for advanced propulsion, places where students work alongside industry pioneers, getting their hands on the very prototypes that will define the next decade of mobility. These centers are crucibles of innovation where a theoretical concept from a morning lecture can be tested in a real-world simulation by the afternoon. This educational shift is the most critical long-term investment in the entire ecosystem. It ensures a continuous pipeline of talent, of minds trained from the beginning to think in terms of fields and forces rather than pistons and propellers. These new engineers will not be limited by the paradigms of the past. They will be the ones to solve the scaling and energy challenges that currently hold the technology back. The quiet vehicles gliding through our future will not just be built with new materials. They will be conceived and designed by a new generation of thinkers, educated in a system that was itself reinvented to make their silent world possible. The silent glide of a thrustless vehicle is far more than a technological marvel. It is an economic earthquake in slow motion. This shift will not merely replace cars with flying craft. It will systematically dismantle and rebuild entire sectors of our global economy. The automotive industry, built for over a century on the principles of internal combustion and mechanical drivetrains, faces an existential pivot. The core product, the engine, simply vanishes. Manufacturers would need to become masters of composite materials, field manipulation, and sophisticated software, a transformation as profound as if a typewriter company had to suddenly start producing supercomputers. Their vast supply chains, currently providing spark plugs and pistons, would become obsolete overnight. The demand for gasoline and diesel would plummet, forcing energy giants to confront a radically different future. Their entire downstream business, from refineries to gas stations, would face a steady decline, pushing them to accelerate their own transition into electricity providers or developers of the wireless power transmission networks that these new vehicles will require. The very map of our cities would be redrawn. Today, real estate value is dictated by location, measured in minutes from a city center or a subway stop. But when travel becomes a direct, three-dimensional flight, the concept of proximity is shattered. A rooftop landing pad in a quiet, outlying neighborhood could become just as valuable as a downtown address, redistributing wealth and population density in ways we can barely predict. The logistics industry would undergo its own silent revolution. Warehouses would stretch vertically, with goods flowing in and out through aerial ports on multiple levels. Delivery drones could bypass road congestion entirely, creating hyper-efficient, just-in-time supply chains that operate with the quiet determination of an automated library. As these old industries transform, entirely new sectors will bloom from the ground up. A new profession of field technicians would emerge, not to change oil, but to calibrate electromagnetic emitters and maintain intricate acoustic transducer arrays. The complex dance of aerial traffic will require a new class of digital air traffic controllers, managing flows of vehicles with AI-driven precision. Energy infrastructure will become a growth industry, as cities are retrofitted with wireless charging corridors and specialized landing zones that function like today's bus stops, but for silent, personal flight. And within the vehicles themselves, a new economy of passenger experience will develop. If your 10-minute commute is a smooth, silent glide above the city, that time becomes a blank canvas for entertainment, focused work, or virtual meetings, creating opportunities for software and service providers we have not yet imagined. The ripple effects extend to the highest levels of global trade. The efficiency of thrustless cargo ships, moving silently across the oceans with minimal energy, could alter the economics of manufacturing and shipping, making distant production centers more viable and reshaping the flow of global commerce. This is not a simple substitution of one technology for another. It is the rewiring of our economic nervous system, where the quietest machines make the loudest impact. This profound silence carries its own set of urgent questions. A vehicle that moves without a sound can also observe without being heard, hovering outside a window with a camera as quiet as its propulsion. The potential for intrusive surveillance is immense, demanding a new legal framework for aerial privacy that we have never needed before. Our laws protect us from trespass on the ground, but how do we define trespass in a sky filled with silent, gliding observers? New rules must be written to prevent these machines from becoming tools of corporate espionage or state-sponsored monitoring, ensuring the silent sky does not become a panopticon. Safety presents another ethical maze. We are trading the known risks of mechanical failure for the uncertain failures of software and field collapse. A car engine stalling is a predictable event with established emergency procedures. But what happens when the artificial intelligence piloting a silent craft experiences a critical error, or when a magnetic field generator suddenly shuts down? The failure modes are not yet fully understood, and certifying these systems for public use will require a level of transparency and redundancy far beyond today's standards. We must build in multiple, independent safety systems, ensuring that even if the primary method of flight fails, the vehicle can still land safely without endangering people below. Perhaps the most pressing ethical challenge is one of equity. Will this revolutionary form of mobility become just another luxury for the wealthy, deepening the divide between those who can afford to glide above traffic and those stuck in it? The initial cost of these vehicles and the infrastructure they require will be high, threatening to create a two-tiered transportation system. The solution must be proactive, not reactive. City planners and governments could mandate that public thrustless transit, like silent magnetic buses, is deployed first in underserved communities, connecting them to jobs and services more efficiently than current options. Subsidy programs could make personal aerial vehicles accessible through shared ownership models, much like bicycle sharing systems today. The goal is to avoid a future where the sky is a private highway for the elite. These are not secondary concerns to be solved after the technology is perfected. They are foundational to its very design. Engineers must embed privacy, respecting features and fail-safe mechanisms from the first line of code. Policymakers must draft inclusive regulations before the first commercial craft takes flight, and the public must be part of this conversation, voicing what kind of silent future they actually want to live in. Quietest revolution will be the one that listens to everyone. The timeline for this transformation is already taking shape in research labs and corporate roadmaps. Within the next 10 years, the first practical applications will likely emerge in fields where silence and precision are paramount. Picture a silent ambulance drone arriving at a chaotic emergency scene, its quiet descent allowing paramedics to communicate clearly and assess the situation without adding to the noise. Envision automated logistics craft gliding through dedicated aerial corridors at night, restocking warehouses and delivering medical supplies to hospitals without disturbing a single person's sleep. These specialized uses will serve as the proving ground, building public trust and refining the technology under real-world pressures. The following decade could see these systems enter the personal transportation sphere. What begins as an elite, high-end commuter service between major city hubs will gradually become more accessible. The convergence of several technologies will act as a powerful accelerator. A new solid-state battery with twice the energy density suddenly makes a 300-mile journey feasible. A breakthrough in artificial intelligence creates a piloting system that can navigate complex urban wind currents with flawless anticipation. An innovation in metamaterials allows a vehicle's skin to harvest solar energy with 40% efficiency. Each of these individual advances does not just add to the whole, it multiplies the possibilities, creating a synergistic leap forward. The ultimate endpoint is a world where this technology becomes mundane, as common and unremarkable as the smartphone in your pocket. Mobility will become a quiet, on-demand utility. The very concept of distance will soften as a trip to a neighboring city becomes as effortless as a short walk. This is not merely a faster car or a quieter plane. It is a fundamental reimagining of our relationship with movement itself, dissolving the barriers of geography and noise that have defined human settlement for centuries. The journey to get here was hidden in plain sight, a quiet evolution in the background of our noisy world. But the destination promises a reality where motion fades into the background, leaving a cleaner, quieter, and more connected world in its wake. This hidden evolution of thrustless vehicles represents one of the most significant yet underappreciated technological revolutions of our time. Its story is not one of a single, thunderous breakthrough, but of countless small whispers in laboratories, a persistent rethinking of the most basic principles of movement. From the earliest theoretical concepts sketched in Da Vinci's notebooks to the functional prototypes silently hovering in hangars today, engineers have fundamentally reinvented motion itself. They did not just build a better engine, they discarded the very idea of an engine as we know it, developing systems that glide, surf, and persuade their way through the world without a single traditional push. This monumental journey could never have been the work of a single genius or a lone discipline. It demanded a symphony of breakthroughs, a convergence of radical advances in materials science, artificial intelligence, and even our understanding of quantum physics. Each field handed a crucial piece of the puzzle to the next, transforming transportation possibilities that seemed like pure science fiction just a single generation ago into tangible, testable reality. As these technologies now mature and begin their careful integration into the fabric of our daily lives, their promise extends far beyond mere convenience. They are poised to transform everything from how we commute and how we design our cities to the very quality of the air we breathe and the soundscape we inhabit. The quiet, meticulous work happening in laboratories and startup garages today will echo through our society for generations to come, its impact resonating in our urban planning, our economic models, and our relationship with the natural world. This future is not one of faster cars, but of a fundamentally different philosophy, where motion becomes silent, supremely efficient, and seamlessly woven into the background of human life. The revolution in how we move has been quietly building for decades, and it is only just beginning to find its voice.